the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. At the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Thank you. I'm happy to be here. It's my first time on the campus. It's very nice. And I want to talk to you about how a lot of monitoring we do at the Delaware River Basin Commission that I feel is sustainability because we're trying to maintain the health of the waters, maintain healthy waters for aquatic life and for human health, for current uses and for future uses, which is, I think, a core principle of sustainability. First of all, I want to have you take your notice of the map. It kind of shows the Delaware River Basin. Hoboken is off kind of to the right of the map. But it shows is that in the headwaters of the basin, it's green, mostly forested, and then that's non-tidal water. And then as you move down, it's up to the right is top right is New York State, and then it moves down past Pennsylvania and between Pennsylvania and New Jersey, and then it moves down past the state of Delaware. So basically, for toxics, it's kind of like three rivers. You have the non-tidal river above Trenton, which is about halfway up, and that water is, for the most part, extremely high quality. It's our special protection water. It exceeds water quality criteria. So you can see that a lot of it is forested area, so it's just, there's the water that's coming into the river is pretty clean. And then as you move down, about halfway down the basin, you're just kind of seeing it's turning yellow. That's agriculture, and then the red areas are the urban areas. And the first urban area, kind of like you'll see, is like the Lehigh Valley, and then you move into the biggest areas: Philadelphia, Camden, and then a little bit north of that is Trenton, and south of Philadelphia is Wilmington. So that I spend most of my time in that area, in the Philadelphia area, where south of Trenton, it gets about halfway down the basin, you switch to a tidal river. So it's a large tidal freshwater river, which is kind of unusual. And then when it gets to where it gets wider, that's what's the bay, Delaware Bay, and that's where you're getting the influence of the marine water. So you're having the mixture of the fresh water and the marine water, so you have an estuarine water. So that makes it complicated when you have that mixture of the fresh water and the salt water, because a lot of the studies are done on fresh water or classic marine water, where you have 33 parts per thousand salt. And that estuarine area, that area in between, it's difficult to assess because you have different species of animals, and the chemistry really gets affected by that interaction with salinity. Oh, okay, so the outline is basically, I want to introduce the DRBC, the Delaware River Basin Commission, talk a little bit about regulations, just to put the context, because the regulations drive our monitoring. And then some of our monitoring goals and how we use the data, and then some of the reporting we do for the monitoring, whether it's for status and trends, whether the current status, what's the current snapshot of the river versus what's the trend over time. And we measure surface water, we measure fish, and we measure sediment. We also do some biological monitoring, primarily macroinvertebrates, small critters that are in the sediment. And we do some ambient toxicity bioassays, which I'll talk about, which kind of measure mixtures of water. The data is used for environmental management of things like legacy pollutants like Pcbs. And we also have a big effort for studying dissolved oxygen in the river. Then I want to talk about, it's kind of a number of different topics I'm going to cover, kind of an overview of what we're doing in monitoring, is how we use the monitoring data in water quality criteria development, and specifically how we're using the latest guidance from the EPA and what would be the latest science on how to assess how available the metals are to the aquatic life. And then finally, I want to talk a little bit about our current surveys in the river for emerging contaminants. We've done quite a few different emerging contaminants. So it's broken into kind of like 4 different sections. But we have 50 minutes. So first of all, the DRBC, why was it formed? Back in the 1960s, there was a lot of water shortages. New York City uses the Delaware River for its drinking water. 50% is drinking water. Philadelphia requires uses the water, and other cities and towns use the water. So there's issues among the states about who was using what water and sharing the water. Also, the Delaware River was extremely polluted. Around the Philadelphia area, there was a dead zone of dissolved oxygen where the fish couldn't swim past that. And there was also issues with serious flooding. So the 4 states, Delaware, New Jersey, Pennsylvania, and New York, along with the federal government, are commissioners for the Delaware River Basin Commission. And the commissioners represent their states and the federal government to make decisions on how to manage water resources in the Delaware River Basin, done on a watershed basis rather than individually by state. So they try to cooperate how to manage the river. So there's a lot of, you can imagine, there's a lot of discussions that go on. So we're an interstate federal compact agency. There was actually a compact written among the states and the federal government to come to agreement on how this commission would move forward. And there were some Supreme Court cases about what to do about water quantity in the river. And one of the reasons we have the DRBC is so you won't have so much time and money invested in legal cases and just trying to get the parties together to agree ahead of time before you end up in court. So I mentioned that the water quality regulations are a driver for a lot of our monitoring. So that's really more than a 50-minute discussion to talk about water quality regulations and criteria. But basically, when you have a water quality standard, it has several components. And one component is designated use. So you have a water body and you say, is that water designated to be used as a water source for drinking water? Or is it for fishing or shellfish collection or wildlife? Is it for recreation, agriculture, or industrial uses? So that's your designated use. Then you also have what's the water quality standards that are developed. And they are developed for national standards by the EPA. And they collect all the data that's currently available on the toxicity of a particular parameter. And then they determine what level is safe in fresh water, let's say, and in marine waters, for aquatic life and for human health. Those water quality standards can have two different types of standards. You can have a narrative standard, or you can have a numeric criteria. The one I described, where they completely look at all the available literature and come up with a number, that would be the numeric standard. A narrative standard is something like not toxic, not present in toxic amounts, or something like that. That would be a narrative standard, that you don't have toxic amounts. So that comes into play in sometimes when you don't have a specific number that you know is safe. So the EPA numbers are developed on a national level, and then each state develops their own criteria for the state. They adopt the national number or they adjust it for their own circumstances. And the DRBC, we actually have our own, what we call stream quality objectives, which are like a state criteria. So we have our own state, our own water quality criteria that kind of harmonize the criteria for the different basin states. So based on those standards and those criteria, then we do a lot of monitoring, and then we assess the water quality to see if it's meeting those water quality standards. We do a lot of observational measurements of surface water, compare it, and then compare it to the standard. So what happens is then the states use that data to come up with what's called a 303D list based on the Clean Water Act, 303 in the Clean Water Act, where you list the water as it either meets the standards or it's not meeting the standards. And then let's say if it's not meeting the standards, then you might need to do something like a total maximum daily load, which is some kind of computation of what loads of a particular parameter are going into the water, and then trying to come up with a model to determine what levels would be an acceptable amount that could be put into the water and still meet the water quality standards. And then there's a lot of NPDES permits, National Pollution Discharge Elimination System, that every individual permit, every individual single discharge into the basin has to meet these different permit requirements. And they can be either technology-based, based on what level can be achieved by some type of technology, or it can be water quality-based effort limits, where they say you need to meet this number in the water, and then you have to do that, either treat your waste more or eliminate the waste. So primarily I work in this area where you're monitoring and assessment and then seeing if whether the water quality is meeting the standards. So it's kind of an iterative, we do an integrated assessment every 2 years of the Delaware River. It's also an important, a third component to the water quality standards, and that is anti-degradation policies. Prevent deterioration of high-quality water. And that is, like what I mentioned, our non-tidal waters up in the headwaters are actually our special protection waters that actually exceed the national standards for water quality. So we have a big effort to determine what's the existing conditions, and then trying to maintain those existing conditions, not have any deterioration. So the water quality standard, basically objectives are protection or preservation of the uses, whether it's for drinking water or for fishing, associated with that water body. And then the protection or preservation of the water quality with the intended existing conditions. So if you have an existing condition, then you want to maintain that even if it's above what some of the national default numbers might be. So overall, it's the preservation of water resources for future or intended uses, and I think that's the core of sustainability. Yes?
What would influence one state to go above and beyond the standard, the federal standard, versus another state that's just like, we're okay with that standard?
Well, sometimes it's public input, the public requires it, and then sometimes it's just there's certain, that maybe like in the Pinelands in New Jersey, the pH is quite low because it's quite acidic, so they have to come up with some type of different approach, implementation of the criteria. But there are, and then different states have a whole development process. Like New Jersey has the Safe Drinking Water Institute that kind of reviews their human health numbers for drinking water. And they have kind of a different process to go through. So basically our monitoring...
I had one more question. You said that it is mainly for the prevention of the deterioration, right? So, but it also says of the existing condition. So, does it mean that it is less of a preventive action and more of a corrective action?
Well, I think it depends where you are. If you're in the upper headwaters of the river, we're in a protective mode, preventive mode. And then if you're in the tidal area near the urban areas, we're in improvement. Okay. Trying to bring up the quality. So our main goals for monitoring, we continue to try to incorporate current scientific knowledge in our monitoring and to use new technology. We are basically trying to measure the regulatory objectives of sustainable, healthy waters. And then we want to have the sufficient information to have a defensible reporting on what's the status of the river and what's the trends. Trends are kind of difficult to do, much more difficult than to do a status. And then this data informs adaptive management. As the information evolves, then the environmental management changes. So that's the adaptive management. And then we trying to do a lot of data coordination with the basin states and other agencies, so we're not duplicating efforts, and then we're sharing the data with them. Okay, so this part of the talk, I'm going to just go over a couple of the main monitoring programs we have. This is the one that's the DRBC is quite known for in our circles. It's sometimes called the boat run, because basically you have this guy sitting on the boat, or a couple people on the boat, and you start down here and you go right up the river, and at each site you have to, they take samples. So it's been ongoing since 1960. So that's kind of unusual to have that long-term study in some type of form in the estuary, the tidal Delaware. 22 sites per month are monitored, and there's a lot of different parameters that are monitored. Routine parameters like temperature, pH, salinity, nutrients, bacteria, metals, and other parameters based on specific studies that we may be doing. All that sampling is done in contract through the DRBC to the Delaware Natural Resource and Environmental Control Agency. They have a lab there, and they have the field crew that's been doing that for years, and we work with them. Sometimes we go out with them for special studies. And I'm going to talk to you this. A lot of this data is downloadable on our website, and I'm going to show you some interesting stuff that recently was done on our website with this data to make it more available for people to access and use. We also look at fish tissue. So here you're seeing the map again, and where you see the icons of the fish, that's sites that we historically go to and we sample for fish. We do a tidal and non-tidal river, and that shows you the frequency of the sampling. It's not every year. It's kind of, it varies based on, is there a project that needs more intensive data, like the PCB TMDL, then we had more frequent fish sampling. But it's tried to do it periodically, and the next sampling was in 2018. So you had 2 fish species, 2 in the tidal area and 2 in the non-tidal area. And these are some of the compounds that we're looking at, bioaccumulative compounds like PCBs, metals, methylmercury. We are measuring methylmercury now. Chlorinated pesticides, dioxin furans, PAHs, metals. So this data is used for things like fish consumption advisories by the different states like New Jersey. We also do sediment periodically, not so often. You can't say that I don't give my all to my work. That's me trying to pull out this heavy Ponar dredge. But these are the things we might be looking at in sediment: PCBs, PAHs, PFAS, and the occur in polyfluoroalkyl substances. I'm going to talk about some more later, and pesticides. And this map just shows you again the tidal river and the bay, and some sites where we measured PCBs, and the red dots, the larger red dots, show the higher concentrations of PCBs, and then the different other locations. And then as far as the biological monitoring goes, look at microinvertebrates. We also look at periphyton. Who knows what periphyton is? That's a tough one. Periphyton is like algae that grows on the rocks in the bottom of the river. And then the phytoplankton is the algae that's floating in the water. So periphyton and phytoplankton, we measure phytoplankton through chlorophyll A. And we do 25 sites in the non-tidal river. Riffles are like if you're driving along a river, or if you've kayaked or canoed, and that's where you see that site where the water is kind of shallow. It's kind of like rippling over the rocks, the cobbles. That's where you get a lot of these organisms. That's where they like to be. They kind of like live under the rocks. So they spend this is the best monitoring. You get a chance to do an internship as a biological, just as the fact that you're right in the water. It's just kind of a fun thing to do. Myself, I do mostly the toxics, but I've done this with people to help them, but it's fun. So, and they also measure different water quality parameters like pH, temperature. So that's done at different sites every 2 to 3 years, and then it's incorporated in our water quality assessment. Okay, this is something I've spent a lot of time on. You can see all these dots are different sites that we have taken surface water samples, and we've sent them to labs to do toxicity tests to see if there's any impact on survival, growth, or reproduction in fish, invertebrates, and algae. So we've done the main stem, the purple squares are the main stem sites, and then all the other yellow circles are different tributary sites. And we've done that in cooperation with the state of Delaware, and we've done it in Pennsylvania and in New Jersey. These toxicity tests are good. They've been going on since 1990 to present. They're good to measure mixtures. So if you're doing the other test, the chemistry, you're looking at individual parameters, and you're comparing it to a specific number that is a water quality criteria. But what do you do when they're all combined? Or what do you do about compounds that you don't even, they're not on your list, that you either don't have a method to analyze for, or you're not analyzing for unknown contaminants. And it also gives you an idea of cumulative effects. There's also all the dischargers do a similar type of whole effluent toxicity test on their discharge for effluent water. And this gives us an idea in the receiving water, in the ambient river, what's the cumulative effect of a number of different effluent discharges. Some of you may be civil engineers or environmental engineers. You probably studied mixing zones. So what happens if you have overlap of mixing zones or just near your mixing zones? So these type of tests help to kind of integrate that type of information. This one, I mentioned that it goes in, you start going into the tidal area. So the lower sample sites here, you're moving from fresh water into more kind of brackish water, and that's been a very challenging area for us to find toxicity tests that are appropriate for those brackish waters. For most of the standard tests are developed for either fresh water or for marine water. So we spend a lot of time developing, modifying tests to try to be able to get an accurate measurement of toxicity in those brackish waters. Okay, so polychlorinated biphenyls, PCBs, they're a legacy pollutant. The DRBC has spent a lot of time on PCBs because in the early 2000s it was definitely identified as a priority concern. Their concentrations were 2 to 3 orders of magnitude higher than the numbers that should be in fish, and there's fish consumption advisories heading the water and sediment. So the DRBC developed the total maximum daily load, TMDL, and it was approved by the EPA in 2003, and then a second stage in 2006. And then how this is being implemented is the dischargers are doing pollution minimization plans. The facilities identify and implement means of achieving maximum practical reductions. A lot of it is trapping sediment. I mean, when you trap the sediment that's being discharged, you're capturing these hydrophobic PCBs. So if you look at the status right now, this recently was reported, that the 10 largest point sources have reduced their effluent discharges of PCB by 70%. And that's what that figure on the right shows. That in 2005, that's the total PCB load from those top 10 dischargers. And now, in 2013, it was reduced 71%. So it's a nationally recognized program. A lot of it involved data, things that are, for the chemists, the very sensitive methodologies are used by all the dischargers, and we were using it when we did the ambient testing. So we could really not get a lot of non-detects. I don't know if you look at the environmental data, a lot of times you're getting a lot of non-detects, and we got really low so we could get really quality data. Everyone basically followed the same procedures and developing a database for this, and then a model was developed. We had an expert panel to help us develop the model, and then it came together and it's making progress. So now the emphasis is on non-point sources, like contaminated sites and stuff. How can we address that? And so that's the next challenge. And that's a whole different approach regulatorily, because that's a whole different group of people that do that type of thing. But from a standpoint of the effluent discharge, it's been a big success. Okay, we talked a little bit about dissolved oxygen a couple times already today. And that's a big issue in many places. There was just something in the news I was seeing today about the Great Lakes, Lake Erie with algae and potential dissolved oxygen issues there. But anyway, in the Delaware River, there's been that was identified as a serious problem back in the before the DRBC was formed, and from 1970s through the 80s, the level of dissolved oxygen in the water in the Delaware River improved tremendously, and that was due to the Clean Water Act and a lot of investment in treatment of municipal wastewater. But you can see in the more recent years that the dissolved oxygen is kind of flattening out, and there are times, especially in the summer, when there's some question about maybe we want to improve that dissolved oxygen in the river. So currently we are examining if current criteria for dissolved oxygen need revision to better protect fish reproduction. And I think earlier we were talking about the difference between fish maintenance and fish reproduction. So currently some of the sections of the river are regulated just to maintain fish population. But if we want to have it that they can reproduce in the river, maybe the dissolved oxygen needs to be a little higher. So in order to do that, we're doing a similar type of approach that we did with the PCB TMDL. We have basically the model. And environmental models, we have environmental modelers. I don't know if no one said they were an environmental modeler, I don't think here, but we have modelers, and they just eat up a lot of data. Can never get enough data. So what we're at is we have the modeling expert panel and a consulting firm advising us on which models to use for the river. And then they have selected a model, and they're basically setting up 2018 will be an intensive data collection year. And then there'll be a lot of data management. And then the model will be calibrated and validated. And then we'll share that. And it's an ongoing process we share with our stakeholders. We have advisory committees that the stakeholders get involved in, different municipalities and industries and environmental groups. And so that's the model. And then from that, we'll have a potentially revised water quality criteria for dissolved oxygen. And then some management options would be developed. And then how would it all be implemented? Would you do a pollution minimization plan, or what to do? So this graph on the bottom right there is basically this more detailed data of the previous figure of the dissolved oxygen, showing dissolved oxygen increasing in the Delaware River right around Philadelphia, right around Ben Franklin Bridge. And that's a big effort right now. It's getting quite a bit of attention. All right, so that's the kind of the major monitoring programs we have going on right now. And then now I wanted to get a little more in-depth into metals, and I've been putting a lot of work into metal bioavailability. And first I thought, I got this, I was at a CTEC meeting, and this Mary Riley, EPA, had this slide, and I thought it was really good because it kind of shows you the adaptive environmental management, or how it changes. You know, that when people who work in regulations, you see a number, and you think that's the number, and it's not going to change, but it's always, the new information comes, and you're trying to improve your regulations, you improve your approaches. So this slide shows the history of the EPA's metals policy. So back in the early 1980s, the metal criteria for how you measure whether or not the metal was a concern in the water was based on total recoverable metals. It wasn't optimal as far as its bioavailability or how it might affect aquatic life, but it's reproducible and implementable. Then in 1985, the EPA policy changed to acid-soluble metals. So then that was an improvement. Then 1993, they went to dissolved metal concentrations. So the base metal criteria was based more on what would be available or bioavailable to the fish or other aquatic life. Then 1994, the water effect ratio was proposed or implemented as a policy, and that's where you compare your lab data to when you take just the surface water and test the toxicity of the surface water, which that kind of gives you a better measure of the different water chemistry in the water and how that ratio between what's happening in the clean lab water and your actual surface water. And then in 2007, the EPA came out with this biotic ligand model. I'm going to talk about that in some detail, that accounts for the variety of water chemistry parameters that impact metals and bioavailability. But it's been very slow to be implemented or adapted by the states. And we'll talk about a little bit some more why. But we've been collecting data to see how we could potentially implement the biotic ligand model. Right now, our regulations say that if you're a discharger and you want to do a site-specific criteria for copper, let's say, you can submit a report using the biotic ligand model. But our standard criteria is not using the biotic ligand model at this time for copper. Not many states have adopted it, 10 years later. So, is anyone familiar with the biotic ligand model? You are. Okay, first of all, what hangs up a lot of people, usually when I give a talk at the end, and then someone will say, what's a ligand? So a ligand is basically something that's going to be bound to it. You know, biological, a biotic ligand is the gill of the fish. The metal binds to that surface, that's the ligand. Or it can be inorganic, like different inorganic, like chloride or something like that. And it can be organic, like dissolved organic carbon. So this model has been developed where they take a lot of toxicity data and the different water chemistry, and they determine how, if you put in these 10 different parameters, primarily dissolved organic carbon, pH, and hardness, temperature, you're going to get a better assessment of what harm this metal is doing at these concentrations to the fish. Now, currently, we use an equation that includes hardness, water hardness. And hardness is basically the minerals in the water, the calcium and manganese are in the water. So as that hardness of minerals in the water increases, the toxicity generally decreases. So this figure there on the right shows you that, okay, the copper CMC is the criterion maximum concentration. That's the acute concentration that should be toxic to fish. That's a micrograms per liter. That's for copper. And then the x-axis is showing you hardness in milligrams per liter. So as the hardness increases, if you look at the blue dashed line, you'll see that the concentration of copper has to be higher in your water to be harmful to the fish. But if you use the biotic ligand model, the BLM, and you see the DOC at the red lines, 2 milligrams per liter is the concentration will be lower than 5 milligrams per liter or 10 milligrams per liter. You'd have to have a higher amount of copper in your water to have the same toxic effect. So they're trying to find out what's truly available to the aquatic life and what is causing harm. It's been slow to be adapted. One thing is you have to measure more parameters than most monitoring programs do, and the people, there's a reluctance in many of the regulators to use the model because they feel like they don't understand the model. So there's also, in 2016, which is pretty recent, the EPA came out with a draft estuarine or marine copper model, and they made it a little simpler. Dissolved organic carbon, salinity, and temperature are the three parameters you need to input into this model. But it's the same idea. It's the competition between the copper trying to bind to the mussels in the surface, in the sediment, in the water, and how do you model that? So again, there's all these sites in the tidal river that we collect data. We've been collecting all the parameters for the biotic ligand model to input into those models, and I've run the models, and I'll give you some preliminary assessment. Okay, this is a complicated figure, but I'm going to go over it. So it is copper in the tidal Delaware River and Bay. It's for illustrative purposes, not for any regulatory compliance. So we're just kind of using the numbers, trying to find out what's going on. So what do we have here on the y-axis? The micrograms per liter, that's the copper. And then the x-axis is the river miles. So up there by 140 on the right side, that's up near Trenton, New Jersey. And then as you move down to 0, 0 is right at the ocean, like Cape May. If you're in Cape May or Lewes, Delaware, if that's a line that goes between them, that's river mile 0. If you ever been on the ferry that goes between them, that's river mile 0. And we have a monitor on that ferry that's collecting data. So we have the two different models, the saltwater BLM and the freshwater BLM. So if we're looking at the left side, that's the saltwater BLM. The blue dots and line is the ambient copper. What's the actual copper concentration in 2015 and 2016 in the river? The 95th percentile, so that would be like the highest, the higher percentile. And then compare that to the red dot, which is our regulatory criteria, and compare that to the green dot, which is the biotic ligand chronic or long-term criteria, CCC. So they're pretty good. The marine one is matching quite well. But then when you move into the freshwater, it gets a little more complicated. I mentioned to you that we have a hardness-based equation that we use to calculate the copper criteria now. But we do it two different ways. First of all, you still have the blue dots and lines. That's the actual concentration of copper in the water. The red dot is our regulatory criteria. That's the number we calculate. It's based on the median hardness value in the tidal river. So that's consistent across all the river miles because it's based on a median number for the entire tidal river. The black dots are if you actually take the hardness from the specific sample that you measured the copper in. So it varies a little bit. It's a little higher down the river where the hardness starts going up, and then it gets lower as you go up the river where the hardness gets lower. So the median is the red dot, and the black dots would be the kind of the variability. Does that make sense? So then, if you get the green dots, it gets a little more difficult with the freshwater model because see those green dots are getting really low below the actual copper. So that seems to be probably a combination of the low DOC and low pH in the upper blue. So if that biotic ligand model was adopted as our criteria, we'd have to do a lot more environmental management to reduce copper in the river. Okay, now just in 2017, EPA has released another approach to metals, bioavailability of metals, and that is for aluminum. So this graph is showing you another approach where they say, okay, the biotic ligand model is too complicated. Some people are saying it's too complicated. This is a little simpler. We're going to do 3 linear regressions. I don't know, if you're not a mathematician, I don't know if that really seems that much easier, but it's a little simpler. Multiple linear regressions. So what are they doing? They have regressions for pH, hardness, and dissolved organic carbon. So basically we have here the concentration of total aluminum on the y-axis, how it's affecting the fish population, the fish in this test, the effective concentration that basically is causing harm to 20% of the fish. And then the x-axis you're showing, if the dissolved organic carbon changes, how does this change the toxicity of aluminum? So basically you're seeing, if you see the solid black line is the model output, and the circle is the actual empirical data. So that would be a pH 6.1 and hardness of 10 to 12 with changing DOC. And then it's done 2 other times with the 2 different model runs and changing the parameters a little bit. For each, the hardness changes from 10 to 63 to 10. So the dotted lines and the triangles are together, and then the dashed lines and the diamonds are together. Does that make sense? So it's basically the same idea that they're trying to incorporate the water chemistry to predict the toxicity, the bioavailability to the organisms. So I've been spending a lot of time on that because I'm an environmental toxicologist. It's very interesting to me, so I don't know. So this one, so now I ran this model also, or this, it's kind of like a spreadsheet that the EPA has out. It's a little different format, but basically you have the same idea. You have aluminum concentrations on the y-axis and the river miles. Now this time I have data from way up to river mile 300. That's like up in New York State, all the way down to it's only fresh water. They don't have a marine one yet. So it's down to 50 when you start getting into marine waters. So in this case, the blue again is the surface water concentrations of the aluminum. So the blue dots are actual samples. It's not a median, a 95th percentile. I think it's actual specific samples. The kind of, and then the red line and dot is our current criteria. You can see it's quite low. It's like 87. It's very protective. And then the EPA multiple linear regression scenarios for chronic criteria would be the green dots. So this is, if that was adopted, we would have, for the most part, only some exceedances down in the most urbanized areas, but up in the headwaters, we'd have no issues with aluminum, because aluminum is present in natural water. So should we be investing a lot of time and energy addressing something that's maybe not a real problem? That's what we're trying to do. We're trying to prioritize what effort, what's really needed to be done. So that's, if we adopted this different, so right now, sometimes when you get the exceedances, people will argue that you're not using the most current science. So we're trying to incorporate the most current science into our regulations and our implementation. Okay. Any questions on that so far? Because we're going to shift gears again a little bit. We're going to talk about emerging contaminants. One area that we've been testing is the pharmaceutical and personal care products. And why are we doing that? Well, we don't have criteria to say exactly what's the safe level, but there is indication that there are biological effects from PCBs. Some of them are very resistant to degradation, so if something's persistent in the environment is concerned. There's a widespread and increasing use of some of the compounds. Wastewater treatment plants are not designed to remove compounds. So wastewater treatment plants are basically designed to remove human waste. It's not for all these organics and things like that. Sometimes we're lucky with the absorption onto solids and things like that. But and then some of the effects to aquatic life have been well documented, especially with the very potent hormones like ethylene estradiol. So again, I'm showing the map. This kind of shows you the area that we're sampling in. This time we only did six sites in 2007, 8, and 9. And then we just last week, the hottest day last week, last Monday, if you remember, it was so hot. We were out there. We redid this sample last week. So it's at the lab right now. So we initially wanted, so a lot of this is very expensive sampling, so we had to limit the number of sites. But we got some very interesting information from these studies. So back in 2007, 8, and 9, I'll show you what we saw. Here again, we have on the bottom, on the x-axis, you have river miles, basically from Trenton down to past Philadelphia. So as you're moving from the right to the left, you're moving past the urban area, and typically with any toxic chemical, you're going to see increase as you move into urban areas. So and then you have the mean concentration. I want to mention that it's in nanograms per liter. So these are very low concentrations. These are trace elements, trace pollutants. So from our study, we studied over 100 different pharmaceuticals and personal care products that we measured. We identified 15 priority compounds that were based on their concentration in the river and their potential to be harmful to aquatic life, that they should get further study. But I want to talk about, there's 3 points I wanted to make. One is note that above river mile 95 is what's designated for source water for drinking water. So generally above that area, we consistently, it's kind of above the most urbanized area, we consistently have low concentrations and the water is safe to drink. As you're moving down further and they're not areas that are not designated for drinking water, you're seeing an increase in the concentrations of a number of these compounds. The metformin, you can see that the kind of the light blue is pretty elevated in a number of different sites throughout, from river mile 68 above. And metformin is an anti-diabetes medication, and a lot of people are taking it, and it's very persistent. So it's basically a post-consumer discharge into the river. The good news is, though, that with the available information, these concentrations are not harmful to aquatic life or human health at these concentrations in the water. The other compound that I want to make note of is the codeine. Notice that that's kind of a different pattern there. You're really just seeing an elevation at larger concentration at river mile 68, rather than it's not all out throughout the river. And it turns out that there are 2 manufacturing facilities, one on each side of the river, one in Pennsylvania, no, sorry, one in Delaware and one in New Jersey, right near that river mile, and they are producing products that contain codeine, so there's some limited discharge from them. But again, there's no data that indicates that these concentrations are harmful to aquatic life, but we are detecting them in the river. Another contaminant of emergent concern that there's a lot of interest in, you may have heard, the per and polyfluoroalkyl substances, the PFOAs, the PFOSs. They have unusual properties. They are both hydrophobic and hydrophilic. And so they are used in a lot of non-stick surfaces, water repellent textiles, stain resistant textiles, and in what these are aqueous firefighting foams that have been used at a lot of Air Force bases and things like that that have gotten into groundwater, things like that. The sources can be direct discharge or indirect, not discharge, but directly the compounds themselves, or indirect from precursors, then becoming these problematic compounds. There is a stewardship program ongoing with the major manufacturers and the EPA excuse me, to reduce the use, actually to eliminate the use of a long-chain PFAS. But there is some concern that the alternatives to the long-chain compounds may not be, still be problematic. Discharges are from both municipal and industrial discharges. They are all persistent in the environment, even the short-chain compounds. Their toxicity varies. There's quite a bit of data for aquatic life, toxicity to liver and thyroid, things like that. There's some data for cancer risk and effects on hormone levels. Yes. Oh, I thought that was a question. Some of them are bioaccumulative, especially the long-chain compounds. And then there's sinks. They end up often in sediment or in biota. So again, here we studied them. We did surface water in 6 tidal sites, 15 in 2007 through 9, 15 sites in 2015. And then we went into the non-tidal sites in 2016. And we had fish samples from 2004 to 2015. That is really a long data set. We started this pretty early. And we've used the same lab. And they had a high quality data from 2004 to 2015. So I am kind of trying to do some, we have been looking at some trends, trying to do some trends on that. And I'm going to show you some of that data. So that we covered the bay, the entire basin. Okay. So here again, on the bottom you have the river miles, down to river mile 6 is almost the ocean, up to river mile 131, which is basically up to Weir Trenton. So that's all the bay and the tidal freshwater river, not the non-tidal river here. We do have some non-tidal data, but basically there was very little there in the non-tidal river. So the concentrations are in nanograms per liter again, and basically the overall message is that these compounds from between 2007, the first time we looked at them, and 2015, they are basically all been decreased in concentration. Again, noting that the drinking water sources above river mile 95, the concentrations are the lowest there. But a couple things do jump out. One is the top there in 2007, that's C9, that's the Pfna, perfluoromanoate. That is a very unusual signal. When I first saw that in 2007, I thought maybe that was a lab error, but we saw the same thing in 2008, and then we were presenting the data, and we found out that there is, it's unusual. Most of you'll see that similar pattern in most urban areas, but that C9 was a little bit unusual. Turns out there was a manufacturing facility in the basin that was discharging the C9. But you can see that by 2015, they're part of the stewardship program. We're not seeing in the surface water, the C9, the Pfna. But we're still seeing the PFOA, PFOS, and the C8 in basically all our surface water samples at low concentration. And now the C5 and the C6, which are the alternatives that people are using instead of the long-chain compounds, they're not actually going up, but they're not going down as fast. So now they are the highest concentration. So we're keeping an eye on them in the surface water. And we've also did some sediment sampling and fish sampling. So I'll show you the fish data. So the main take-home message is fish fillet. Now we did the fillet, that's the muscular fish, because we're concerned with fish consumption. A lot of people study these compounds in the fish blood or the liver, which you'll actually get higher concentration. But we're concerned about consumption, so this is all fish fillet data. The 2 tidal species and the 2 non-tidal species. So in 2004, that's the numbers we saw. We have pretty elevated PFOS in the non-tidal water. And that's kind of odd because, well, it indicates how bioaccumulative the compound is, because the concentrations in the non-tidal water are quite low. But that particular fish is bioaccumulates quite readily. So it varies by the species of fish you're measuring. It varies by whether you're measuring fish tissue, the fillet, or the blood, or the liver. It varies by location in the river, and it varies by year. So if you compare 2004 with our most recent data in 2005, the PFNA is basically not being seen in the fish now. So that's good. That's the one that was so high in the previous water samples. But we're still seeing the PFOS, and that's more about, again, that PFNA of the C9 is more like an industrial discharge, where the PFOS is more like a post-consumer. It's just getting released from so much use of that product by different people in textiles and things like that. Okay, this is the last emerging contaminant. This is another one there's a lot of interest in, the PBDEs, the polybrominated diphenyl ethers. It gets confused a lot with, these are flame retardants that are put into foam and like furniture and clothing so that they won't catch on fire. Where the other, yes, time's up, 5 minutes? I think I'm almost done. These, the other compounds, the PFAS, were used to stop fires. Once this fire's gone. So they're used in a lot of consumer products. The biggest concern is indoor dust, but there is concern about dietary exposure eating fish. So that's why we were looking at we started looking at water, but we didn't see it in the water very high at all. So they are bioaccumulative and toxic and persistent, and they can cause harm. There's a voluntary phase out, and EPA has action plan and a significant new use regulations, and the state of New York has banned these compounds, some of these compounds. So this graph is actually done by a Westchester University student. It was her keystone project for a master's, so I just wanted to mention that because we do have a lot, you'll see that we have a lot of data, so if you're interested, you want to try to do some unusual analysis of the data, we'd be happy to work with you on some, if we identify a project. But this is the PBD data. You can see the different years. Basically here, she took all the 2 different tidal fish species, catfish and perch, and combine the different sites and basically get one number for each year. And you can see that the concentration is going down. She also did some risk assessment on the data and some statistics on the data. So that the trend on these compounds is also going down in fish, which is good. So overall, we have water quality assessment reports that we do with this data. We do cooperative reports with what's called the Partnership of the Delaware Estuary, which is more of a trends reports. And then I mentioned the models that we're doing, Pcbs and eutrophication for dissolved oxygen. And I don't know now, since I don't have, let me see if I can get this open. I don't know if I, no, let's see. How can I? Want to go? Yeah, let's see that. Can you get that going?
Yes.
Ron?
Yes.
When it fiddles with this, can you talk about your internship program?
We do have interns primarily in the summer. Then I just use this here. So we have interns that do help us with the monitoring in the summer. And so I just wanted to show you this. This is all online where you can see the different parameters. You can look at different years and you can download all the data. It's all not really showing us the. There you go. So you can see different figures that can be generated with the data. So we do have an internship program with help us monitoring in the summer, quite a bit, and it's also the potential to work on projects with oh, is that going to close everything?
Yeah,
No, don't do that.
that's okay.
I still have a couple slides.
No, that would just close the
Just that
process.
one? Okay. I meant to check that out before I started, so. So if you're, we'd be interested in working with you if you're, would like to get involved in water quality in a river. So some of the threats, and I didn't really talk about it, is the salinity, increased salinity in the river from road salt. That's a big problem nationally. I did talk about pharmaceutical personal care products. Also, natural gas development. We have a lot of, there's a lot of concern about that right now in the basin. So basically, we're doing a lot of monitoring just to see what's the magnitude and the frequency of some of the contaminants and how we did a lot of baseline monitoring, so we have data before any natural gas development would have potentially occur in the basin, and then what would happen afterwards, measuring things like barium and things like that, and salts. And I just wanted to give a shout out to all the people who are involved in our group, and we do have, I wanted to mention that we do have interns, currently we have 2, and that's about it.